Okay, let's talk about the applications of rnns. But first of all, let's talk a little more about language model. Why should you care about language modeling? Because language modeling is a benchmark task that helps us measure our progress on predicting language use. Now, what does benchmark mean? It is kind of standard task that we do to measure how well we are doing on the task of natural language processing. And language modeling is a subcomponent of many NLP tasks, especially those involving generating texts or estimating the probability of text. And we saw this example, predicting typing. And in the case of speech recognition, the way we speak some words are different from how we write those words. I cannot come up with the correct example, but in Korean, when we say 발음, it sounds like 발음. And this one also contains another meaning, like the right thing. Therefore, when you just hear the sound 발음, you cannot distinguish whether it's the first one or the second one. In that case, you need to think about the context. And to consider the context, you need to use language modeling. And language modeling helps speech recognition system to distinguish ambiguous words. And when you do handwriting recognition, some people, it's not easy to recognize words when it's written by hand. Like when you see this word, it looks like S. However, some people say, oh, isn't it 5? Therefore, you need to think about the context. In that case, language modeling can help. And spelling, grammar check, correction also apply language modeling. And when you train some language models, then that model can actually detect the author of some texts, because each people has their own style of writing, and RNN models or language models can predict the author. And when you do machine translation, there might be some ambiguities. Then you can also correct or improve the probability of predicting the next word. When you do summarization and dialogue, similar things, principles apply. And everything else in NLP has now been rebuilt upon language modeling. And nowadays, people are very well known about ChatGPT. And ChatGPT is also one type of language model. And as you can see from this example, language modeling enables a lot of variety of tasks in NLP. And other RNN use cases are like this. You can use RNN for sequence tag. And when you do part of speech tagging, you can use RNN very well. And this one distinguish whether the given word is noun or a verb, etc. And to do so, you need to think about the context, the left and right context as well. And some words have the same form when it's used as verb or noun. And you need to think about the context to distinguish whether it's a verb or noun in that sentence, okay? And you can also use RNN to classify sentiment. Sentiment classification is broadly used in the field of review classification. When you buy something online from an online shopping mall, then you leave sometimes reviews. And researchers want to analyze whether your review is positive or negative. And if it's negative, then the product manager would analyze, oh, this product is not good for customers. Then we might replace this one with better ones. Anyway, sentiment encoding receives the review and classify whether it's positive review or negative review. Basically, how to compute sentence encoding, the basic way is use the final state like this. And even better way is take element-wise max or mean of all hidden states. In that way, we can encode the sentence into a abstracted hidden state like this. And we can also do question and answering. For example, this is the question. What nationality was Beethoven? And here we're given the context. And we need two systems. The first one is to encode the question, and the second one is to encode the context. Or you can use the same encoder for both the question and context as well. And there are numerous neural architectures that do encoding for the question and context. And as you can see, this task is somewhat more complicated than the previous ones. That means you need more complicated neural architectures to solve this problem. And you can also use rnNLM to generate text and speech recognition. And this input audio is basically time sequence data. And that is exactly where RNN can be used. And here, you can process this input data and make this one as hidden state. And in the case of normal or ordinary language model, the first hidden state was initially zero initialized. However, in the case of speech recognition, you can condition this hidden state using the encoding of this input audio. And this is an example of conditional language model. And this one write down describe the sentence spoken in this audio file. Okay. And you can also generate description for an image. In the previous case, we conditioned this RNN with this audio file. However, in the case of image captioning, we condition with the embedding of this image. And after that, this RNN will generate the description of the image. It starts from the start token, and then it generates the first word, and you pass this first word to the RNN as the second input, and it generates the next input, next output, het, and then it goes to RNN like this. And here you can see we are using both CNN and RNN in combination. And because this one involves both image processing and text or natural language processing, NLP, this task is sometimes called multimodal task. Okay, we're using just not unimodal, but multiple models at the same time. In more detail, when we're given this test image, we pass this image to our CNN like this. And we don't need to use the last fully connected layer or softmax layer, because our goal is not to classify whether this one is a straw hat or not. but we just want to encode information in this image. Therefore, we remove the last two layers and we calculate the embedding up to this layer. And after that, we pass this information to our RNN like this. And this is normal RNN. However, we are adding another factor. And then it starts to generate the description. And we sample the next word and sample the next word and proceed like this. And we finish sampling when the last token is the end token. This is sometimes EOS, end of sentence token, or just end, whatever you want to use, it's up to you. All right, these are some examples of image captioning. As you can see here, a man riding a dirt bike on a dirt track. It's quite accurate. Of course, there are some failure cases. In this case, however, a man in a baseball uniform throwing a ball, even though he's catching a ball. Okay. So there are some failure cases, of course. And in the previous slide, we talked about just normal question and answering. However, in this case, the question and answers, all of them are in the form of text. However, in the case of visual question answering, the input is not just text, but an image. And the question is about the image. What endangered animal is featured on the truck? And the answer is a bald eagle. Okay. And as in the case of image captioning, this visual question answering task needs to understand both text and image at the same time. Therefore, this task can also be called multimodal task. All right. And we need to encode two information. The first one is the image. We need to encode the image first, and we also need to encode the question itself. And after that, we can pass these encoded information to a fully connected layer and do some softmax, and we can get the answer like this. And you can also think about visual dialogue. In general dialogue system, this is sometimes called chatbot. Now we are communicating using texts. However, in the case of visual dialogue, we can give image to our chatbot, and we can talk about the image as well. Nowadays, ChatGPT handles both. It will be able to handle both image and text as well. And nowadays, foundation models are becoming more multimodal, not just text and image, but it can also process speech or audio signal like that. And there is another task called visual language navigation. Previously, we only cared about visual navigation. In this case, we only care about images. However, in the case of visual language navigation, we also think about language. And you can give instruction in language. This is very helpful when we implement intelligent agents like robots. We want our robots to go to some place like, hey, go to the dining room and do something like clean up the table like that. And our robot needs to be able to understand both the text or the spoken language, and it also needs to be able to understand the surrounding environment using visual perception. And it has to be able to perform visual language navigation. Okay, so this is another example of multimodal task. And in the case of visual question answering, there is a known dataset bias issue. However, this one happens to all types of tasks. For example, if the answer is either yes or no, but in the data set, the answer yes consists of 70% and no comprises like 30%, then when the model is confused, then it will tend to answer just yes, because it's probabilistically more plausible. That could happen. And we talked about just RNN, a single layer RNN. However, to this RNN, what we feed is n number of batch. This is the batch size. And T is the time step. And we also pass D, this encoded vector. Let's say word vector. Then what we get after we pass through RNN is same number of batch and the time index and the dimension of hidden size. And what it means is we can pass this vector through another RNN. Okay? As we did for CNN, like we stacked multiple CNN layers, convolution layers, say conv. We can do the same for RNNs. Therefore, we can stack multiple RNNs like this. So that's what multi-layer RNN is about. And as we stack more and more convolution layers, the representation power improves. And the same thing happens to multi-layer RNNs. We stack more RNNs, we get more representation power. And there is another architecture called bidirectional RNNs. Here it is how it works. We have two RNNs at one layer. The first one is called forward RNN. The second one is called backward RNN. For forward RNN, we do the same as usual, like pass the inputs in the normal order. However, in the case of backward RNN, it goes in the reversed order. So the last word first and the second last word next, like this. It goes in this direction. Why do we need to do this? This is an intuitive example. Let's say we want to analyze the sentiment of or the meaning of this terribly. Okay? And when we just think about the forward context, the movie was terribly, then we might say, oh, this terribly might mean negative thing. However, when we think about the backward context, then we can easily see that it is positive because it's about exciting moment. Okay. Therefore, we sometimes need to think about both forward and backward contexts. That's why we need to use bidirectional RNNs. And on time step T, we calculate the forward RNN hidden states like this. We just pass normal X inputs. And for backward RNN, we use a reversed arrow on the top like this. And we pass the same input in the reversed order. And what we do is just concatenate the hidden states like this. And we regard this as the hidden state of a bidirectional RNN. Okay, this is what we pass onto the next parts of the network. All right. Okay, think about this question. And let's check the answer together. Okay, what is the answer? The answer is the second one. The first one is correct. Language modeling is a fundamental and input task that aids other tasks such as predictive typing, speech recognition, and summarization. The second one is somewhat ambiguous. However, image captioning with a pair of CNN and RNN requires a F layer attached to the CNN. Because in the previous example, I showed an example with two fully connected layer with the last fully connected layer removed. However, we don't need FC layer at all. FC layer is basically for classification in the case of CNN. However, even though we don't have FC layer, it's okay. Okay, this might look somewhat ambiguous. However, we don't. This image captioning architecture doesn't require a FC layer. Okay, next topic is gated RNNs. What does it mean by gating? First of all, let's think about the gradient flow of vanilla RNN. And so this is how we calculate the RNN hidden states. The backpropagation from HT to HT minus 1 multiplies by W, actually the transpose of W, okay? And when we want to calculate the gradient of HT in respect of HT minus 1, we first need to take derivative of hypertangent and calculate these values. However, the problem is the RNN structure architecture repeats that our computation. So H1 affects H2, and H2 affects H3, and H3 affects H4. That means H2 also affects H4, and H1 also affects H4. That means to calculate the gradient in respect of H1, we need to think about H4, H3 times H4, H3 and H2 like this. So we're going to multiply these values from T2 to the time step T like this, okay? That's what it's about. So when we calculate loss 4, loss 3, loss 2, loss 1, all the loss to calculate the derivative of W in respect of loss, we need to think about all the time steps because W involves in all the process of calculating H1 to H capital T. Then why is it a problem? As I told you, to calculate loss at time T, I calculate the derivative of loss at time capital T in respect of W, we need to think about all these factors, like HT minus 1, HT minus 2, and up to this point. And this one involves these calculations. And here, we're going to apply W multiple times. Okay, so you can think about it as this one. And I told you this one is hypertangent derivative times W. And when we multiply these value multiple times, and if this value is because there is hypertangent H, this one is almost always smaller than 1. And when you take power of like 0.9 to the power of 10, it becomes 0 very easily. That means we can lose all the gradients, meaning vanishing gradients. And if we don't have any gradients, that means our network does not learn anything meaningful. And what if we assumed no nonlinearity? Then similar thing happens. Even though we remove the nonlinearity, hypertangent, if this one, we need to take power of capital T minus 1. And if the largest singular value is larger than 1, then the gradients are going to explode. Think about 0.2 to the power of 10, like this. And the largest singular value is smaller than 1, like 0.9 to the power of 10. It becomes easily 0. It becomes easily diverged. And these two cases are called exploding gradients and vanishing gradients. And to resolve the issue of gradient exploding, we introduced gradient clipping. Therefore, we can solve this problem quite easily. Then what about vanishing gradients? We need to change the architecture of RNN to resolve the issue of vanishing gradients. And let's think about vanishing and exploding gradients once again. To calculate loss, the derivative of loss in respect of H1, we need to think about this loss as well, with this vector, and this vector, and this vector. And as I told you, if these values are small, then vanishing gradients happens. And when we omit the nonlinearity as before, as in the previous slide, here, that's what it's about. If we assumed sigma is the identity function, then we can just remove this part, and BHT over THT minus 1 becomes WH. And you can calculate gradient in respect of H like this. And you can think about the eigenvectors of W. And you can write this as this. Okay, and this becomes 0 very easily. And the nonlinear activations entail similar problem. We saw this in the previous slide, okay? And I told you the gradient signal from far away is lost because it's much smaller than gradient signal from close by. So model weights are updated only with respect to near effects, and we cannot think about the long-term context. That's the problem of vanishing gradients. For example, let's have a look at this one. This is one of LM task. This one wants to predict the next word here. And let's have a look at this example. When she tried to print her tickets, she found that the printer was out of toner. She went to the stationery store to buy more toner. It was very overpriced. After installing the toner into the printer, she finally put in her, what is the answer? We all know that tickets should come here. However, tickets here are very far from this place. Like, how many words are there? Like 10, 20, like 25. However, our rnns can only think about 10 time steps. In 25 time context, it's impossible. It's very easy question, right? However, because our computational model, RNN, can consider only 10 time steps at a time, it cannot solve this easy problem. And it has to learn long distance dependencies, okay? And why is exploding gradient a problem? We saw this in the previous sessions. For example, we are updating the parameters following this loss plane. Then if gradient is very big, then rather than going to the minimum point like this, it will go like this. We saw this example in the previous sessions. And you will see infinite numbers or NaN, not a number. These two are very irritative when you implement some models on your own. And you're going to encounter a lot of cases of inf and NaN. Okay, the gradient clipping, we already implemented this algorithm. And how are you going to fix the vanishing gradient problem? The main problem is that it's too difficult for the RNN to learn to preserve information over many time steps. And in a vanilla RNN, the hidden state is constantly being rewritten using this equation. Then one idea to solve this problem is, how about an RNA with separate memory? Then this RNA model can store some important information to this cell and constantly update new data, new information using the hidden state. And that is the first approach. And another approach is using attention or residual connections and etc. Okay, so introducing a memory system to RNN is done by long short-term memory. This came out in 1997, but it's still effective. Vanilla RNN looks like this. Given the previous hidden state and the current input, they are multiplied by a matrix and passes through hypertangent. And that generates the next hidden state. However, in the case of LSTM, we do similar thing. First, concat the previous hidden state and the current input and passes through multiple paths. And what are these? We have 4 gates, and we have one cell, which stores important information. And we also have hidden state. And using these 4 gates, we are going to control which information to pass through hidden state and which information to store in our cell. What does it mean by 4 gates? These W have different form, like 4H by 2H. And this one, after passing through this matrix, the input and previous hidden state, they all pass through different activation functions, sigmoid, 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 and hypertangent. And then we get 4 gates. And this G is called gate. Gate. It's somewhat ridiculous. However, it determines how much to write to cell. Gate determines how much to write to cell. And what is I? This I determines whether to write to cell. So this input gate determines which information to write, and this G gate determines how much to write to cell. And this 4-gate gate gets multiplied to previous cell state and determines which information to erase. Therefore, this cell state gets updated by 2 mechanisms. Preserving previous information or updating new information using input gate and G gate. And the forget gate determines which information to preserve and which information to forget, and how to update new information using this input gate and gate. And what about output gate? It determines how much to reveal cell to this hidden state. Okay. All right, this is how it looks like. First, we concatenate the current input and hidden state, and we multiply these concatenated values with W, and it passes through some activation functions, and this forget gate gets multiplied to the previous cell state and determines which information to erase. And then new information updates the current state, cell state. And this output gate determines how much to reveal the information in this CET to hidden state. Okay, and we're going to use these hidden states to generate outputs. And as you can see here, backpropagation from C2 to CT-1, unnear element-wise multiplication by F, no matrix multiplication with W. And as you can see here, this generates a new path for gradient. This gradient is not interrupted. Okay, and this is similar to residual connection. And do LSTMs solve the vanishing gradient problems? The LSTM architecture makes it easier for the RNN to preserve information over many time steps. How many time steps? Around back, 100. In the case of vanilla RNNs, it's about 10 to 20. It's way better than normal RNN. However, it's not infinite. If the F equals 1 and the I equals 0, then the information of the cell is preserved indefinitely. By contrast, it's harder for vanilla RNN to learn a recurrent weight matrix that preserves information in hidden state. However, LSTM does not guarantee that there is no vanishing or exploding gradient, but it does provide an easier way for the model to learn long-distance dependencies. Okay, it's not perfect. However, it's way better than vanilla RNNs. And I told you this gradient flow is similar to ResNet. And you can also introduce some highway networks to improve the performance of LSTM even more. If you're interested, you can have a look at this paper. And of course, there are other RNN variants. GRU is one of them. And people generally choose between LSTM or GRU. The computation, more and less. And the performance is slightly like, I don't know exactly, but 1 to 2% higher than GRU. So according to your application, you need to determine which one to use, LSTM or GRU. And there are some research, active research, try to find the best or optimum RNN architecture. Okay, let's implement LSTM together. Okay, class LSTM. We first need initializer, like this. And we need forward. Here, different from normal vanilla RNN, we need another parameter, C pref, cell pref. And we need two upstream gradients, DH next and DC next. Think about how you can implement this LSTM structure. First, let's implement initializer first together. I mean, the parameters that are going to be WH, WHB. Pretty simple. WH and MP0 light B. Okay. And we need to store some cache for backpropagation. Think about how you can implement forward and backward on your own, and see you in the next video.